Aerodynamics and Aircraft section that will be on the FAA commercial private exam, written exam. So this one says, to hold an airplane in a level flight at airspeeds from very slow to very fast, the pilots must coordinate angle of attack and thrust. That makes sense. Okay, figure 5, point C. The intersection of dashed lines at point C is the airspeed where the minimum usable turn radius is predicted and represents the aircraft's maneuvering speed. So let me go ahead and increase the size of this. Oops. The intersection of the dashed lines at point C, this line and this line, is the airspeed where the minimum usable turn radius is predicted and represents the aircraft's maneuvering speed. Yeah, if this is max structural cruising speed, this is top of the yellow, or top of the green. This is the red line, so this is all the yellow. So yeah, this would be maneuvering speed, because if you're going any faster and make an abrupt movement, you can cause damage. So if you're going at this speed, 125, below that you won't cause damage, which is the gray. So we can go to the next. The correct statement. Select the correct statement regarding stall speeds. The airplane will stall (27 knots higher in a power off gear and flaps up 60-degree bank than a power off gear and flaps up wings level configuration. So I guess we look at the power off gear and flaps up 60-degree bank. Okay. Power off. And they're giving us knots, so 92. So power off, gear and flaps up. So that's 92. And then over here we go look at power off, gear and flaps. Power off, gear and flaps up. Power off, gear and flaps, wings level. So we look over here. So 92 minus 65. That's how we figure out this question. And that's 27. So 27 knots. So you just got to do that math. Okay. At a given airspeed, what effect will increase in air density and have what effect will an increase in air density have on lift and drag? Well, if you're going faster, there's more molecules, so you'll have more drag and more lift because there's more pressure on the bottom of the wing. So yeah, it says that in order to maintain lift at a higher altitude, an aircraft must fly at a greater true airspeed for any given angle of attack. Okay. VNO is defined as max structural cruising speed. So that's top of the yellow arc. Sorry, top of the green arc. I think NO is normal operating range. Stalls occur due to airflow separating from the surface of the wing due to exceeding critical angle of attack. Correct. That just makes logical sense. So refer to figure 2. Select the correct statement regarding stall speeds. Select the correct statement regarding stall speeds. With gear and flaps down and power on, the airplane will stall. Gear and flaps down and powered on, the airplane will stall 9 knots higher in a 45-degree bank than in level flight. So you look at 56 minus 47. So yeah, 56 minus 47 is 9. So that's correct. Okay. Select the correct statement regarding stall speeds. With gear and flaps up and power on, the airplane will stall. Get our figure back. Gear and flaps up and power is on. So level versus 60. 76 minus 54, that's 22. So that's how we get that answer. The ratio of an airplane's true airspeed to the speed of sound in the same atmospheric condition is Mach number. That's easy. The aircraft's wing exceeds the critical angle of attack when it stalls and experiences a loss of lift. That's pretty easy. Okay, get our figure back up. Gear and flaps down and power on. Gear and flaps down, power on. At a 30-degree bank, which is this one, the airplane will stall 12 knots lower with the power on than the power off. So we look at this number, 50 versus 62. 12 knots lower. The power off, you stall at 62 knots. And if power is on, with the gear and flaps down, you stall at 50. So that's a difference of 6. What best describes a condition in which airflow over any part of the aircraft first reaches Mach 1.0? That's a critical Mach number. So that's when airflow is going over the top of the wing faster than the airplane's true airspeed is, because those molecules are accelerating due to the, I think it's Bernoulli principle. So yeah, that's the critical Mach number. So the airplane might be going 0.8 Mach, and it might already be at the critical Mach number. Critical Mach number is the condition where airflow over any part of the aircraft reaches Mach 1.0, which is basically the speed of sound. What is ramp weight? Ramp weight is zero fuel weight plus usable fuel weight. So that's the zero fuel weight plus all of the usable fuel on board. So you've flown to an airport in the mountains. Your airplane is parked at the ramp at 5,000 feet MSL. The ambient temperature is 90 degrees, so it's pretty hot. The altimeter is set to the local altimeter setting and indicates 5,000 feet. That evening, the temperature plummets to 50 degrees Fahrenheit, so 40-degree drop in temperature. Unless reset, the altimeter will indicate 5,000 feet MSL. So what they're saying is that difference in temperature won't cause a difference in the altimeter setting displayed. So the explanation of this is if the temperature had plummeted to the point where application of the altimeter correction table was necessary, then the answer would be different. However, since the temperature is still well above freezing, and 50 degrees is above freezing, the altimeter temperature error is minor. So unless a huge change in local barometric pressure had occurred at the same time, the altimeter will still indicate field elevation. So just remember to keep that same 5,000. All right, we're going to pause the video.